Wait, you don't have to. I didn't just. I did some weird stuff. Don't worry about it.
I was trying to build.
As long as those 5 lines are there, the box is there. That's all.
Okay.
Yeah. Oh. Oh.
Spaceship overrated.
Generally important in that meeting. You would like me to
That makes sense. It is research.
It is.
It makes sense because no, because we haven't gone in, but they could but like it makes sense. Not even great, so you just.
Yeah, and I mean,
Just people something around. Like.
that's what we were trying to do.
Yeah, it's like.
It's pretty steep. Right, and then we can. You can skip it.
All right, it's 4 o'clock. Let's go and get started. Right, good afternoon, everyone. How's everyone doing today? Good, doing good. All right, and so today is end of week 3. So we have one more lecture this week. And so my plan for today is we're going to finish up our lecture with an unconstrained classical optimization. I have a couple more examples using in multiple dimensions. So hopefully that will be interesting. I think, and then after that, we'll start our lecture on constrained optimization. See how we can bring in equality constraints into that. All right, so as a reminder, homework 1 is due tonight. So make sure you are doing that. I think most people are at least almost done at this point. And so if you have any final questions on it before midnight tonight, you go ahead and send me an email, and I'll try to get back to you. Okay. Homework 2 is almost ready, so I'm just about finishing up the solutions for it. I just have maybe about half a problem left, and so once I finish that, it should be posted by probably sometime. Okay. Okay, so I think that's all my announcements. Are there any questions I can answer before we get started? Okay, all right, so let's go and get started. And so to begin with, let me go ahead and scroll up a little bit here. So I'm just gonna go through kind of the review from last time fairly quickly, just so that we can kind of jump into an example. Okay. All right, and so at the end of class on Tuesday, we started talking about multivariable optimization. Okay. And we're going to solve these multivariable problems using the classical. Okay. And so what we were saying was that in the multivariable scenario, when you have 2 or more design variables, the process, at least in spirit, is not all that different from our single variable case. And so the first step we're going to do is we're going to take the first derivative of our objective function and set it equal to 0. Okay. The only difference here is that in the multivariable scenario, we're going to take multiple first derivatives because we have multiple design. And so for each design variable that you have, you're going to take a first order derivative, first order partial derivative with respect to that variable. Okay. And doing so will give you a system of equations that you can solve for that'll give you the optimal point. Okay. Or optimal points, I should say. Okay. Step 2 in the process is to determine whether those extrema that you found in step 1, whether they were maxima, whether they were minima, or maybe they're neither, maybe they're a saddle. Okay. And so the way that we do this is we compute something called the Hessian matrix, which is a matrix of second order partial derivatives. Okay. And so we have kind of the general form of the Hessian that we went over here, and then we have the 2D case box at the bottom. That's the one we'll generally kind of use the most, just because with these multivariable optimization problems, the amount of algebra that goes into them is usually quite large, and so I'm not going to ask you to do more than a 2D problem. Although I do want to show you how they scale up to higher dimensions. And so I want to show you kind of the 2D form specifically, just because that's the one we're going to use in our examples. But just know that if you are going to scale these up, then the Hessian is going to grow inside as well. Okay. And so for a 2D problem, our Hessian is going to be a 2x2. For a problem with 3 design variables, we have a 3x3 Hessian, and so on and so on. Okay. And then what you do with the Hessian is that you have to determine whether this Hessian matrix is going to be positive definite, negative definite, or semi-definite. And that's going to tell you whether or not you're doing one of our maxima, minima, or okay, so we kind of left it here last time. So all this should be in your notes already. And so the first thing I want to do today is first of all show you how do you determine whether a square matrix is positive definite or negative definite, and then we'll jump into examples. So I think the 2 examples that I have today will probably take up the majority of the time, and then from there we'll jump to constraint optimization or whatever amount of time. Okay. All right. Any questions on this? This is just kind of the recap. Okay, all right, so let's see how we determine whether a Hessian matrix is positive definite or negative. Okay. And so what we want to do is we have our Hessian, which is a square matrix, and we want to find out whether it's positive definite, negative definite, or similar. Okay. So there are multiple methods for this, and so if you've taken probably an advanced linear algebra class, you've probably gone over this concept before. And so there are more ways to do this, and we can dive deeper into what these mean. But I don't want to dwell too much on it, just because we're only using it as part of our optimization. So I'm going to go over kind of the algorithm that I think, or the method that I think is kind of most convenient. But if you have other methods for determining the positive definiteness of a matrix, definitely feel free to use them. Okay, so to determine whether a matrix is any of those things, I find that the easiest way is to find the determinants of the principal submatrices. So what are the principal submatrices? So let me draw a 3 by 3 matrix. So a 3 by 3 matrix, it's a little bit bigger than kind of what we're going to be working with. I think it kind of gives you the idea of the principal submatrix. Okay, so first of all, what you should know is that if you have an n by n matrix, and so you have a matrix with n rows and n columns, there are going to be n principal submatrices. Okay? And so for a 3 by 3 matrix here, that means we have 3 principal submatrices. And you'll see why kind of very quickly. All right. And so the way to get the principal submatrices is to kind of start in the upper left-hand corner, and then kind of highlight all the square matrices that kind of come along that direction. Okay. And so the first principal submatrix is always very easy. And so the first principal submatrix is just the top left entry of the matrix. Okay. So we usually call this A1. Okay. And so the first principal submatrix is just the top left. Technically, even though it's just one number, we can say that it's a 1 by 1 square matrix, which is kind of cheeky, but it works for this. So that's always the easiest one to do. Just look at the top left entry of the matrix, and that's your first principal submatrix. From there, you kind of move on to the next biggest square matrix that you can make that also includes that top left entry. Okay? And so you basically kind of draw squares of increasing size. Okay? A2 here is our second principal submatrix, and it's that 2 by 2 in the top. A1, 2, A2, 1, A2, 2. The second submatrix. And then the final submatrix is just going to be the, it's always just going to be the entire matrix itself. Okay. Until we make this box just kind of bigger. This. With A3. In this case, A3 is the final submatrix just because this is a 3 by 3 matrix. A3 is just the entire matrix. I'm not going to write down the matrix. All right. And so once you have all the submatrices, what you're going to do is you're going to compute the determinant of each of these submatrices. Does everyone remember how to compute the determinant of a 2 by 2 matrix? You only need to know 2 by 2. So 3 by 3 starts to get a little bit stuffy. It's not hard. It just takes long. It's kind of annoying to do. Exactly right. So to take the determinant of a 2 by 2, you're going to multiply the two entries of the main diagonal, and then you're going to subtract the product of the two entries of the off diagonal. So let's start from A1. So A1 is just the first submatrix. So it's just one entry. So the determinant of that is just going to be very the determinant of A2, like we just mentioned, is going to be the product of the two entries on the main diagonal. Okay, so A11 multiplied by A22. Okay, so these are the two entries on the main diagonal. Then we're going to subtract the product of the two entries on the off diagonal. A12, A2. And for the 3 by 3 matrix, we're probably not going to see it in this class, but you can look up an algorithm to solve for 3 by 3. But basically, it means the way I usually do it is I kind of walk off, or I kind of start from the top left, and then you multiply that entry by the determinant of this 2 by 2 matrix, and you subtract the same thing, but for the second entry and the third entry. It's not a hard process. You've probably done it before, especially if you've done cross products before. But it's just a little bit tedious to do. And if that were the only thing that we're doing, I'd say let's do it. But we're doing this in the middle of an optimization algorithm. We're doing a lot of other calculations too. So usually not worth it to do it. If we ever have a 3 by 3 or optimization algorithm with 3 design variables, we probably need it. Okay. Anyway, back to the schedule program. So now that we have the determinants, how can we use these to determine if they're positive? Okay. And so a matrix is positive definite. if the determinants of all the submatrices are greater than 0, then our matrix is positive. And so in order to get a positive definite matrix, the determinant of A1 and the determinant of A2 have to be greater than 0. A matrix is negative definite if the determinant of A1 is less than 0. And so the very top entry of the matrix should be less than 0. Okay. And all subsequent determinants of the submatrices alternate in signs. So what this means is that determinant of big A1 has to be less than 0. Determinant of big A2 has to be greater than 0. Determinant of big A3, if added, had to be less than 0. Right? And so we alternate. Right? So we go negative, positive, negative, positive, negative, positive. In all other cases, and so if you have a pattern of determinants that don't match either of these, then we just say the matrix is semi-definite. Right. So we can use the Hessian matrix to determine whether the extrema that we find is either minimum or maximum. And so we'll see that kind of illustrated next. All right, any questions on this before we jump into an example? Okay, all right, so let's do an example. First, multi-dimensional. All right. So let's say that we have a following configuration with 3 springs and 2 carts on wheels. Draw. On the left side here, we're going to have a rigid wheel. On the right here, we're going to have a cart. We'll assume that that cart has frictionless wheels, so we're not going to consider friction in this case. Let's say that we have a second cart that's smaller. And so connecting these carts are going to be 2 springs. We have 1 spring that attaches to the wall and attaches to the smaller cart, just like that. And we have another spring That's going to go from the smaller part to the big part. In addition to this, we have one longer spring which attaches the bigger part to the wall. We have kind of a weird contraption with 3 springs and 2 carts on the wheels for whatever reason. All right, so let's label these and let's give them some property values. All right, so this top spring we'll say has a spring constant of K1. The bottom left spring will have a spring constant of K2. And the bottom right spring will have a spring constant of K3. So we're going to assume that all 3 springs are different. Okay. The smaller part I'm going to label as cart 1. The bigger part I'm going to label it as cart 2. So the other thing that we're going to do to kind of give this system a little bit interesting behavior, we're going to take the bigger part and we're going to pull it to the right. And so we're going to apply a horizontal force P, and we're going to pull this entire assembly to the right. So of course, doing that, applying a force in that direction is going to cause both carts to move. Okay. And so we can measure its displacement using 2 x. And so we'll say the displacement of part 1 is given by x1, and the displacement of part 2 is going to be given by x2. X1, x2 are in response to the force. Okay. All right, so that's the geometry we're working with on this problem. Any questions on just kind of the drawing here and the tables? All right. And so for this problem, what we're interested in is solving for the values of x1 and x2. Okay, so we're going to assume that we know all the other variables in the system. We're going to know all the spring constants and the values of force P. Okay. And so we want to solve for how much the carts displace. And so at first glance, this doesn't seem like it's an optimization problem. It seems like it's a kinematics problem, right? Or dynamics problem. But we can actually formulate this to solve it like an optimization problem. Because what we know from solid mechanics is that when you apply some kind of external force to an elastic system, which is what we have here, then the system is going to deform. And the exact amount of deformation, the exact pattern deformation that results is one that minimizes the potential energy. Okay? So in other words, what we can say is that x1 and x2, their values are going to be set such that the potential energy of the system is minimized. And so I underlined that word minimize because, whenever you're in this class and you hear the word, maximize or minimize, that should kind of, it's like the chat I sleep meme, and then when you hear the word minimize, suddenly go with optimization in use. All right, and so we can formulate this as an optimization if we make our objective function the potential energy. Okay. This will become our objective. Okay. So let's go ahead and do that. And so let's go ahead and write out our equation for the potential energy. And so I'm going to use a symbol U. So it's going to be a function of x1 and x2. Okay. And we're going to write out the potential. Okay. And so in this case, we have 3 springs. Okay. And so the potential energy that's stored in the system is going to be stored in those 3 springs. So we should have at least 3 terms here that correspond to the 3 springs. And so if we remember from physics, the potential energy in a spring is 1/2 K times its displacement squared. So this right here is the potential energy for spring 1. Okay. Because spring 1 has a spring constant of K1, and because it's attached to the bigger part, the bigger part has the deformation x2. And so the potential energy in spring 1 should be 1/2 K1 x2 squared. Okay. And so we can do the same thing for spring 2. So spring 2 is the one with the K2. So that's 1/2 K2 x1 squared. We use x1 here because the smaller part has its displacement equal to x1. And then we have the potential energy for spring. So spring 3, you have to be a little bit careful because it's a little bit different than the others. Okay? And so we look at K1 and K2, right? K1 and K2 both have its left-hand side attached to the wall. And so the total amount that spring is going to stretch is completely based on just the parts that they're attached to. So x2 for K1 and x1 for K2. K3 is in a different position because its left-hand side is attached to the smaller part, whereas its right-hand side is attached to the bigger part. Okay. And so the total amount that K3 is going to stretch is actually going to be the difference between these two. So this is going to be x2 minus x1. And so for the potential energy, we're going to have 1/2 K3 times x2 minus x1. All right, so that's the potential energy in all the springs. One last thing that we do have to add here, though, is that we do have a force that's acting on the system as well. Okay, and so we have to account for the work that external force is. So that's going to be a minus E x work. Because P is being acted on part 2, the bigger part, and so the amount of distance that force acts on is x2. So we take the product of the force times the displacement, that's going to give us work. So that is also going to affect the potential. Okay, so that's the objective function that we're going to work with. All right, any questions on this? Okay, all right. So we have our objective function. Okay, we know that we're doing a multivariable optimization because we have two variables here, x1 and x2. And so let's go ahead and start our method. Okay, so step one. Step one of our method is going to be to take the first partial derivatives of u with respect to the two design variables. We have partial u, partial x1, and partial u, partial x. So let's do partial u, partial x1 first. So partial u, partial x1. We're going to take the derivative of all terms of x1. If it doesn't involve x1, we just ignore it. And so this first derivative here is going to be k2 x1 minus k3 times x2 minus x1. It's going to be equal to 0. And then we have partial u, partial x2. And so we perform that derivative, we get k1 x2 plus k3 x2 minus x1 minus 2. And this is also equal to 0. Okay. And so by performing those derivatives and setting them equal to 0, we now have two equations that we can solve for our two unknowns, right? So our two unknowns are x1 and x2, and we have two equations that we can use to solve for their values. Okay. Just for convenience, just because I'll be referring to them later, let's call this first equation equation 1, and I'll call the second equation equation 2. Okay. Here's where the algebra gets a little bit tedious. All right, so let's solve equation 1 for x2, and then we'll plug that into the bottom. Okay. So solve the first one for x2, then what we have here, starting from 1 here, is k2 x1. I'm going to leave that on the left-hand side. Since we only have one value for x2 here, let's go ahead and move that to the right. And so we have k2 x1 plus, so we have a minus minus, okay, plus k3 x1 is equal to k3 x. All right, so we're going to divide both sides by k3. And so dividing both sides by k3 gives us x2 x2 is equal to k2 x1 plus k3 x1, all divided by So now that we have the value for x2, so let's go ahead and plug that into equation 2. If everywhere we see x2 in equation 2, we're going to plug that in. And so equation 2 starts with k1 x2. If we plug in x2, we have k1 multiplied by k2 x1 plus 3 x1 K3 plus K3 times quantity of x2 minus x1. So once again, we're going to plug in for x2 here. So K2 x1 plus K3 1 3 1 minus E. So we kind of have a mess here, and so it's not a very clean problem. But let's go ahead and continue on. Because now what we have here is an equation of just one more unknown. Right? The only unknown in this equation is x1, because we've already substituted for x2. From here, it's just just kind of have to work through the algebra. And so let's distribute all the terms, and then we'll simplify it. All right, and so working on the first term here, we have nothing to cancel out. So take 1, 2, 3, 1 plus. Next term, we have a K3 up top, a K3 up bottom. So we have K1, X1 plus. We have another K3 over K3 plus K2 X1 plus. We have a K3 times K3 divided by K3. So it's a lot of Ks. So 2 are going to cancel out. And so we just have a K3. We distribute one more K, so then we have a minus K3 X1, and then minus P, and all this is equal to 2. All right, so now that we're at this point, let's go ahead and simplify. So we can see here that we have a K3 X1 positive, K3 X1 negative. So these are going to cancel out. Okay. Let's take the P and let's move it to the other side of the equation. And then another thing we're going to do is we're going to take X1 and factor it out of all these. All these have an X1. Okay, so let's do all 3 of those steps. X1 divided by A1, A2, plus A1 plus A2. All this is equal to E. Just to simplify this a little bit. So this step is optional, but it makes your solution look a little bit cleaner. Okay. So what I'm going to do is I'm going to multiply this entire equation by K3. And so if we do that, that just kind of cleans up that fraction. We have X1, A1, A2, plus A1, A3, plus A2, A3, A2, K3. And finally, we can divide by everything in that parentheses to solve for x. So we get this x1 is equal to E K3 divided by K1, K2 plus K1, K3 plus K2. It's a lot of algebra, but of course, we have everything in variable. So that's one nice thing about the classical method, that if you can, if the problem is simple enough, you can actually get your solution in variable form like this, which has a lot of advantages. So now we can actually test this solution for different values of the spring constants. We just have to plug it in. Plug it into this expression. All right. Any questions on how we obtained this result here? All right, so very quickly, let's take this result and let's solve for x2. And so based on our earlier relationship, we know that x2 is equal to k1 plus k3, k1 plus k2, k1 plus k3 divided by k3 times x1. And so let's take our expression for x1 right there and multiply it by k1 plus k3 over k3. Okay. So we have k1 plus k3 divided by k3 e k3 k1 2 plus 1 3 plus 2 k3. Luckily for us, the K3s are going to cancel out. And so this kind of makes a very nice, clean result. And so this gives us x2 equal to E multiplied by product of sum of K1 plus K3 divided by quantity 1, 2 plus 1, 3 plus 2. And so those two results there, that's our optimal solution. Okay. So those are the values of x1 and x2, which are an extrema of our potential. Okay. I'll go ahead and spoil it a little bit. It is a minimum. So this is the minimum of our potential energy, but we have yet to show it, right? And so to actually show that this is a minimum, we have to compute the Hessian matrix and make sure that it's positive. Okay. So let's go ahead and do that. So we're going to compute the Hessian, and we're going to show that it's positive. Okay. And so remember, the Hessian matrix is our matrix of second order partial derivatives. So let's compute all the partial derivatives of our objective function in this case. All right. So the first partial derivative that we're going to compute is partial squared u partial x1 squared. Okay. All right, so we're going to go back up to our first derivatives. So let me scroll here. And so we know from earlier that the first order derivative is this. We're just going to take one more derivative here with respect to x1. Okay. We take one more derivative with respect to x1, we get k1 plus k3, or excuse me, k2 plus k3. Let's take the second order derivative with respect to x2. And so we go through, this is equal to k3 plus k1. And so we can't forget our cross derivative. So our cross derivative is partial squared u, partial x1, partial x2. Okay. And so to get this, we take our objective function. First, we take a derivative with respect to x1. then we take a derivative with respect to x2. Okay, so you kind of alternate the derivatives. And so if we do that, for this problem, we get a value of minus k. Okay. All right, so using these values, we can compute the Hessian matrix. Okay. Yes.
So the cross derivative is basically the product of the first derivative with respect to x1 and x2, right?
Exactly.
Yeah.
Yeah, so you can go either way. So, from the first step here, we compute both.
We do have the value, yeah.
Yeah, and so you can either take this first result that I've circled in blue and take the partial derivatives with respect to x2, or you can take the second expression in which we took the partial derivative with respect to x2 first, and then take the derivative of that with respect to x2. You're gonna get the same. Okay. Okay, so you can go either. Okay, so let's go ahead and plug in our second order partial derivatives here. So in the top left, we have k2 plus k3. On the off diagonal, we have minus k3, k3. And on the bottom right, we have k3 plus k. So now that we have the Hessian here, we can compute the determinants of each of the principal submatrices, right? And so we only have two here, right? So we have just a 2x2 Hessian matrix. And so our A1 needs the same color as earlier. So A1 is going to be this guy right here. So A1 is just K2 plus K3. Of course, we're doing everything in variables here. But remember, K2 and K3, those represent the spring constants for two of the springs in our system. Okay? And a spring constant cannot be negative, right? It doesn't make sense to have a negative spring constant. You probably break some rules of physics. Okay? And so if we know that both K2 and K3 are both individually positive, then that means A1 must be positive. So we're off to a good start, right? And so in order to be positive definite, all of these determinants must be positive. So the fact that we start with the positive one is good. Okay, let's look at A2, or the determinant of A2. Since this is a 2x2 matrix, the A2 is going to be our last principal submatrix. So it's just going to be the determinant of the entire matrix itself. Okay. And so if you remember from before, to get the determinant of a 2x2, you take the product of the two main diagonal entries. You get K2 plus K3, multiplied by the entry in the bottom right, K3 plus K1. And then from that, we're going to subtract the product of K minus K3 squared. So that's the computation of this. All right, and so we have to do a little bit more work here because of the presence of a negative sign, we can't just outright say that this is going to be a positive number. So let's do a little bit more algebra and let's show that this actually indeed is a positive. Okay. So let's FOIL this out. If we FOIL this out, we get 2, 3 plus 2, 1 plus 3 squared plus 3, 1. And we can't forget the extra term here, so we're going to minus A3. All right, so we have good news. And so we have a positive K3 that came out from the foiling. We have a negative K3 that came out from the off diagonals, and so these two are going to cancel out. Okay. And what we get is determinant of 2, 2, A2, 3 plus A2, 1 plus A3. So this is nice because this result here, because we know that each of the k's individual, K1, K2, K3, they're all going to be positive numbers. Okay? And so since we have all positive numbers here and they're all either multiplied by each other or added together in this expression here, we know that this has to be a positive number. All right, and so we have the determinant of A1 is positive, we have the determinant of A2 is positive. All of our submatrices have positive determinants, and so this means that our Hessian is positive definite. And if our Hessian is positive definite, what does that tell us about our extrema, right? And so the values of x1 and x2 that we found out earlier in this problem, that tells us that x1 and x2 represent a minimum of our objective function. Right, and so that concludes this example, right? And so in part one, we solved for the value of x1, x2. We know that that's an extrema. We didn't know that that was a maximum or minimum. And then in step two, we computed the Hessian, and we found that it was positive definite. And so that tells us that our solution for x1, x2 is indeed a minimum of the objective. All right, any questions on this example here? Okay. All right, so I did have one more example for multivariable optimization, but I did want to make sure I get the constrained optimization to this. So I am going to skip that example, but I do want to leave a note here just so that you can take a look if you want to see it. Okay. There is one. One more example for multivariable optimization at the end of lecture notes 02. Yeah, question.
So we found two extremes, right? One for x1 and one for x2.
Those two together is one extreme.
Okay.
Yeah.
That's certainly fun.
Yeah, because remember, we're doing a multi-dimensional optimization, so a pair of points that consists of one. So actually, the last example is actually interesting, because it actually gives you a situation where you have multiple optimizations. You actually will have 4 points in this example. Maybe we'll go over it maybe next week if we have time. But I did want to at least kind of start the concepts of constrained optimization, just so that we can kind of continue that conversation. All right, so if you go to the Canvas website, you download lecture notes 02. At the end of those lecture notes, there's one more example that kind of goes through. It's the reason I'm kind of skipping it is that it's a little bit tedious, just because there's a lot more algebra involved, but it's the exact same process that we went through. I thought it'd just be but if you wanted to look at another example to see how it's done, especially as you start working on homework 2, you can post it soon. Then there's one more example there. Okay, but for the last 20 minutes of class today, I did want to start talking about constrained optimization. Because when we went over all the graphical optimization stuff, we talked a lot about constraints. Then all of a sudden I said, don't worry about constraints. And so, I want to bring them back just to kind of show you that the constraints do still exist, and how, and talk a little bit about how we can incorporate that into our algorithms that we've learned. So let's talk about constrained. Classical. All right, so just to refresh your memory a little bit, when we talk about constraints in optimization, a constraint is a mathematical restriction on the values that the design variables can. And so in the example that we did today, and in all the examples, most mathematical examples that we've been doing the last 2 weeks, there's been no restriction, right? So we just say that, whatever values that our algorithm comes up with, that our derivative tells us, those are the options. But in reality, when you have these kind of practical optimization problems, there are going to be restrictions in terms of what values the design variables can take. A lot of times it's based on cost, in terms of how much material you can actually buy or something like that. And so we have to learn how to account for these in our procedures. Okay. And so what we learned was that constraints, they come in 2 flavors, and so there's equality constraints and inequality constraints. Okay, so equality constraints are defined by a set formula with an equal sign. And so most of the times, or at least the most interesting equality constraints, these formulas are going to involve more than one design. standard form for these is you have some function g. Okay. G being a function of the design variable. So remember, I'm bringing back this notation of x vector. Okay. So x vector is a vector that represents all of our design variables, and that is, this function is going to be equal to 0. So some examples, quick. So let's say that we have an optimization with two design variables, and so maybe we have an equality constraint that's 5x1 and 6x2 plus 7 is equal to 0. Okay. That would be an example of an equality constraint, and so we have a function here that's a function of both design variables, x1, x2, and equals 0. Okay, so the key here is the equals. Another example, maybe we have, let's do a little bit more interesting. So let's have 6 sine of x1 plus 4e with x2 plus 7 equals to 0. Okay. And so the mathematical form that we use for x1, x2 can be anything complicated, right? So here we have sines, we have exponents, we have square roots, whatever, and sometimes, most oftentimes we'll see, squares. As long as you can put it into a form where, it equals 0, then that serves as the equality. All right. The other type of constraint that we have are inequality constraints. And so inequality constraints are defined by a formula that has an inequality sign. And so, there's lots of different inequality signs. We have greater than, we have less than, we have greater than or equal to, less than or equal to. Okay. And so technically all of those are valid. So you can use all of those as inequality constraints. But there is a standard form. So the standard form for inequality constraints is to use it less than or equal. Also, the standard form, very similar to the equality constraint, is to have one side of the equation equal to 2. Okay. So I forgot to mention this on equality constraints. So sometimes you'll be given formulas where it's not equal to 0. Oftentimes, especially as we use some of the methods that we're going to learn in this unit, you need to rearrange it so that it does. Same thing with the inequality. So the general form for these is going to look like this. Okay. And so we have some function L, which is a function of the design variables x, is less than or equal to 0. Okay. More specific examples, we can turn any of the equality constraints up there into inequality constraints. So we have 5x1 6x2 plus 7 equal to 0. Or even something very simple. The one thing that you'll see often is that when we have situations where the design variables have to be positive, you might see inequality constraints that look like x1 greater than 0, x2 greater than 6. And of course, those aren't standard form. And so in order to get those into standard form, we'll have to multiply those equations by -1. Okay. Take these to standard form. This x1 less than or equal to 0. U. All right. So those are the two types of constraints that we have. Okay. We'll tackle these kind of one at a time. And so to start with, we're going to start with the equality constraint, just so those are a little bit easier to work. Probably sometime, definitely not on Tuesday, but maybe next Thursday, we'll start talking about inequality constraints. Okay. Any questions on these? Okay. All right. So let's start with the equality constraints. All right, so equality constraints are kind of unique because they define a set relationship. Okay, so there's no wiggle room, right? And so whereas inequality constraints, because of the nature of the inequality, there's a lot of wiggle room there. But for equality constraints, there's a set relationship that's kind of immovable. And so, when I describe it like that, it kind of makes it seem like this is very inflexible, right? But in reality, this is actually a very, very good thing. Because what this does, you can almost think of this as like kind of adding an extra equation to your problem, which actually makes your problem simple. Okay. And so what we can say is that when you have equality constraints, most of the time, what that's going to do is that this is going to reduce the dimensionality of the problem by 1 per equality constraint. And that is a very, very good thing. So what do I mean by dimensionality, right? And so we kind of just finished talking about multivariable optimization, right? So optimization where you have 2 or 3 or more design variables. Right? And so what we saw, or kind of what I talked about, is that the more design variables that you have, the more difficult your problem is going to be because it's going to require an optimal. Okay. And so when I say dimensionality, what I mean really is the number of independent design variables. But when you add equality constraints into the fold, you can actually reduce that dimensionality. So instead of solving a 3-dimensional or a problem with 3 design variables, you would effectively only solve one with 2 design variables and maybe only 1. Okay. So let me give you a very, very simple example. So let's say that we have a 3-dimensional optimization problem with 3 design variables. F. So let's say a 3 design variables of x, y, and z. And let's say that our objective function is x squared plus y squared plus z squared. So the 3D optimization. So if we go by the methods that we just learned, we know that we have to take at least 3 first partial derivatives, and our Hessian is going to be 3 by 3. So that's going to be a huge hassle. But let's say that this problem also comes with some constraints. And so the terminology that we usually say is that, we're usually given an objective function, and we say that this objective function is subject to certain constraints. Okay? Let me do a very, very simple one. So let's say that the value of x is constrained to be 2 by an equality constraint. All right, and so just for whatever constraint, we know the value of x has to be 2. If we know the value of x is 2, let's just go ahead and plug that into our objective. Okay? And so this is now equal to 2 squared plus y squared plus z squared. Okay? All of a sudden, our objective function is no longer 3D, right? And so since we plug in a value for x, now our objective function is only 2-dimensional. We just have 2 design variables, like y and z. So that's fantastic, right? And so instead of solving, a 3-dimensional problem where we have, a 3x3 Hessian, now we have only a 2x2 Hessian, which is a lot easier to, or I should say, a lot less annoying. Right? And so you may see this and you're like, all right, that makes sense. But that only makes sense because our constraint here was very distinct. I will show you that even with a more complicated, quality constraints, you can still reduce the dimensionality of the problem. And so let's say that we have an equality constraint, 3y plus 7z minus 10 equals 0. Right, so our equality constraint here is a little bit more complicated. It involves, both of the remaining variables. But what we can show is that this is actually going to reduce our dimensionality by 1. Okay? Because what can I do with this? Let me solve this equation for y. With 3y is equal to 10, 7z. Okay? So y is equal to 1 over 3, and 7z. Let's plug this back into our objective. So our objective function f is equal to 2 squared plus y squared, and so we just solve for y. So this would be 1/3 n minus 7z 1 squared plus. So this quantity here is what used to be y squared. If we look at the amount of variables that we have left, we only have 1, right? And so y is gone now, right? So we've already substituted in y. And so now all of a sudden we have just a 1-dimensional optimization problem in Z. Okay? So this is even better, right? So now we don't even have to compute the Hessian. Now we can just solve it as a 1. Okay? But you have to be careful with this, okay? And so, we can see that each time we add an equality constraint, we reduce the dimensionality. Okay? What you'll never see, or almost never see, is you'll never see an optimization problem with the number of equality constraints equal to design variables. you should never see it equal to the number of design variables, and you should definitely never see it be greater than. Because what happens if we add one more constraint to this? So if we add one more constraint, let's do it very simple. And so let's say that we add another equality constraint that z is equal to 6. If we plug in z is equal to 6, all of a sudden our objective function would be no more. Now we just have f is equal to some constant, and we have nothing to optimize. Right? So what you end up with is an over-constrained system. Okay? And so that's always really important. So equality constraints, generally they're a good thing. They help our lives out a little bit. But if you have a system with too many, then you kind of ruin, kind of over-constrain, and all of a sudden you have nothing left. All right, any final questions on this? Okay, all right, so that's all we got time for today. So next week, we're going to start with a couple of examples in terms of how do we solve constraint optimization. And then we'll go from there. All right, so thank you guys for coming today. I hope you guys enjoy your weekend, and I will see you guys next week. Yep. I think that was one of those.
Yeah, I don't know.
K2. Yeah. Yeah, so this one, so I think the last one. Yeah, so that should be. Yep. Yeah, because you want to go for the curve that has a more negative. And so this starts at 250 revision. And so as you go kind of this way, you can see the value of that. And so just kind of the way that we define optimistic, we might go. Okay, so ideally, we like to use the first to have the most value, but it doesn't cross the next one that has crossed. So actually, any point on this curve would be a point. The reason I say a bound point is that somewhere between these two curves, other curve, that probably intersected right there. And so somewhere between f is equal to 1500, maybe it's like f is equal to 60, something like that. And so f is equal to 60 will probably just intersect the value. So that would be the most common. But out of the 5 that's presented here, this one is the most common. You can pick anything on the cards, but just just based on kind of based on what we know for the bound point is easier to if you take this point here, then the value for x2. Okay. Thank you. Yeah, you can submit this. Yeah, just send me an email. Okay. Yeah.